In this last video, we'll take a look at how our MongoDB database is deployed. If we look at our mongodb.yaml file, this is perhaps the most complicated one with 4 different parts, but don't worry, we'll break them down one part at a time. We'll start with something familiar, which is the service component. This is very similar to the service component that you've seen in the RabbitMQ deployment, which is in the last video, except that we're selecting the pods with the app label app:/MongoDB, which is a new label. This line, again, must match the template field in our replica set. Speaking of replica set, you might have already noticed that we're using a replica set instead of the deployment objects that we used in the last video. Our goal here is to run a simple storage solution by running a simple pod that runs the database. For such a singleton application, both replica set and deployment resource will both work, but we can of course simply create the pod, but in the case of a node failure, the pod will not be rescheduled onto another node. So it's almost always better to use a higher level resource, even when managing just a single pod. I would not recommend running such configuration in production if you have any apps that's large scale or customer facing, but for smaller applications or maybe for internal applications, the complexity trade-off here is definitely worth it. If you have a larger scale application or if your application is customer facing, you might need to use something called stateful sets. We won't be able to get into stateful sets in this video series, but maybe in a future video series we'll get into it. For many smaller scale applications, or if you're just building an internal app, or if you're just building a demo here, the complexity trade-off of not using stateful sets and just using a singleton application is definitely worth it. So if you look at this YAML file, everything should be pretty similar to the deployment resource from the last video, but there are a few differences. First, we create a volume called MongoDB-data by using the persistent volume claim. You might not be familiar with the persistent volume claim for now, but we'll go over it here in a minute. Notice this volume is created on the pod level, meaning all containers within the pod can mount this volume. Next, we mount volume inside our container definition, and the mount path is data/db, which is the default path for MongoDB. Alright, so next we'll look at our persistent volume and the persistent volume claim. So storage in Kubernetes is somewhat of a unique resource in the sense that we must assume both the role of a developer and a Kubernetes administrator. As a developer, we need to access resources such as CPUs, memories, or storage without actually knowing how the resource are provisioned. But developer also wants to simply ask for like 1 CPU or 1 gigabyte of disk space. Such decoupling is just one of the central ideas of Kubernetes. But Kubernetes admins, on the other hand, needs to know how and where those resources are coming from, right? So up until this point, we only work with resources such as CPU and RAM, which are basically automatically provisioned by GKE. But for storage, we must do it ourselves. So what we'll do is we'll first create a network attached storage. Then we'll attach the storage that we make in Google Cloud Platform to our Kubernetes cluster using something called persistent volume. And then finally, we'll put down our admin hat and pick up our developer hat and use the persistent volume claim to claim the storage that we created. So alright, so let's first assume the role of the Kubernetes administrator and create a network attached storage. Since we're already using Google Cloud, we'll just use the Google NAS storage offering called GKE persistent disk. So first we'll run the gcloud container cluster list command to get the compute zone of our clusters. Our disk is going to be in the same zone as our cluster. Once we have the zone, we use the command gcloud compute disk create, followed by the size, zone, and the disk name. It's going to give us a warning that our disk is too small, but we'll ignore that for now for this demo. So once the disk is created, we'll create a persistent volume resource in Kubernetes using our YAML file. Be sure to put the name of your disk, which for me is MongoDB, into the PD name field. It is also important to tell Kubernetes that the technology behind your compute disk which for me is GCE persistent disk, because Kubernetes actually supports a lot of different type of network attached storage. The field access mode determines if the disk can be read or written by multiple nodes or a single node. At this point, we can put our administrator hat away and become a developer again. We'll create a persistent volume claim, which is called PVC. In the PVC, notice there is no mention of the specific technology that is used by the storage. All we need to do is use a selector and bind it to our persistent volume and specify how much storage space that we need. This completes our setup for the storage. However, keep in mind that we're using a very simple setup. So if you're interested, look into dynamic provisioning and definitely stateful sets. This is the end of the video series.